Let me summarize the module which we have studied in last 4 to 5 weeks. We started with analyzing the genomics data, where we looked at it as a read, and first problem we look at it, given a set of reads, how we can actually assemble genome from the scratch or de novo assembly of genome. And we showed that this problem can be formulated as finding a path on graph. Either it is a Hamiltonian path or either it is a Euclidean path, or either it is a Hamiltonian path or it is a Eulerian path on the graph. Then we look at genome alignment problem, where we try to align either globally or locally two sequences. And again, we showed that this is again finding a path on a cyclic graph. And this problem can also be formulated as solving as a dynamic optimization problem or dynamic programming problem. And we provided an algorithm to solve genome alignment problem. Then we move to the biological networks, how we can actually generate a graph out of biological networks and see this graph as a data. So it's a graph data, we have looked at it. And here our major aim was to learn graph representation using graph structure and node features. And also we saw that age feature can be used. Particularly, we were interested in two kinds of tasks. One is the node embedding task of graph representation and the graph embedding of task of graph representation. Why we are interested in either node embedding or graph embedding? Because there are node related tasks. We want to classify node in certain cases. We want to predict certain property of nodes. In that case, node related embedding is important. On the other hand, we are also interested in graph related tasks. Given a graph, what is the label associated with it? Given a graph, what kind of value it actually induces? In that case, we are interested in graph level tasks. Hence, graph embedding becomes important. That's why we have looked at graph as well as node embedding as a graph representation learning task. We have learned set of algorithm to perform shallow embedding for a node related task. And we saw that some of these node related tasks can be performed well with a shallow embedding. However, it has its own limitations, which we discussed why they cannot be used for many graph level as well as node level tasks. And hence, we move towards graph neural networks and learned that we can perform far better embedding using the deep learning approaches on node level tasks as well as graph level tasks. What we did in the graph neural networks, I started with understanding the philosophy of graph neural networks, and we studied the building blocks of graph neural networks. Recall that we have not studied GCN, graph convolutional network, or graph attention networks, but we have studied how they can be constructed using the graph filters. We study different kind of graph filters, which can be used along with activation layers and pooling operations to create graph level embedding. graph filters are good enough to create node level embedding or defining the node features. However, when we are interested in graph level tasks, we need a pooling operations, and we studied different kind of pooling operations, which provides us quotient graph structure and ultimately features for a particular graph. Also, we discussed different kinds of graph neural networks, including message passing neural networks as well as directed message passing neural networks. And at the last, what we have looked at is applications of these graph neural networks in drug discovery and design. We looked at different kind of problem associated with drug discovery and design and how AI and deep learning approaches we have studied in this particular course can be useful to solve them. We have looked at how drug discovery can be useful to make up property predictions, protein interface prediction, drug target binding affinity predictions, or drug-drug interaction predictions. So all these problems we have seen, which can be formulated as deep learning over a graph, and it can be useful to solve this problem. Throughout this course, I have actually used several materials. Well, these three materials stand out where I referred a lot. I would like to thank Dr. Tang and Ma for providing the deep learning on graphs notes available, which is now published as a book. Similarly, Dr. Hamilton's book on graph representative learning, which notes are again provided by them. Thanks to them for which is now published as a book, and also Professor Yuri and Professor Zitnik for their tutorial on deep learning for network biology, which also discuss more applications of network biology in different problems associated with biology in healthcare. So, thank you.